welcome everybody. Is this thing working?
Yeah.
Yeah, so yeah, welcome everybody to this distinguished lecture that we're going to receive today. My name is Shane McIntosh. I'm an associate professor here, and it's my great pleasure to welcome Earl Barr. Earl Barr is a professor of software engineering at University College London. He's currently on sabbatical at Google DeepMind in Montreal. Yeah, but we won't hold that against him, okay? He received his PhD at University of California, Davis. Earl's research interests include artificial intelligence for software engineering and vice versa, debugging, testing, and analysis, game theory, and computer security. His recent work focuses on probabilistically quantifying program equivalence, probabilistic type inference, and dual channel constraints. There's a bit here about dodging vans and taxis that I'll leave to Earl to explain, but Earl has received about all the best awards that we have in the software engineering community. He's received two 10-year retrospective awards, one at ICSE, the top conference in the area, one at MSR. He's received 6 distinguished paper awards, ACM 6-off distinguished paper awards. So somehow his talk has to live up to the hype. Good luck.
Thank you, Shane. Thank you for that introduction. Okay, today I'm going to tell you about a new way to view code, which I call dual channel constraints. And then I'm going to show an extended application of it to the problem of automated program repair. Code has 2 audiences, machines, which must run code correctly. Do what? And okay, so machines and humans who must understand the code in order to maintain and extend it. Machines read the code by directly executing it. Humans, on the other hand, build a model, a mental model of the computation, which, to a first approximation, builds a gist of the code from a skim of the programming constructs used in it and the natural language fragments and typesetting and whatnot. So from the two audiences give rise to 2 goals. Programmers try to write code that is both correct and easy to read and write. And these goals, in turn, give rise to 2 channels. The algorithmic language channel, which consists of everything in the code needed for it to run correctly. We call this the AL channel. And a natural language channel, which contains the natural language cues and stylistic choices that help programmers understand the code. And these 2 channels share tokens. And because they share tokens, they interact. So let me concretize this with an example. This is a little snippet of Python that implements the sieve of Eratosthenes, an algorithm from antiquity. And the function name in the algorithmic channel, it's just a label that uniquely identifies a unit of functionality. But in the natural language channel, the name in good code, the name summarizes the function so that you don't need to read the function body. You can, at a glance, you look at the function label and function name, and you have a guess at what it means. Layout tells you at a glance the control flow. So control flow is fundamental in the algorithmic channel, but this typesetting gives it to the developer in the natural language channel at a glance. Parameter order is in the algorithmic channel, and the alignment of the names that are passed in the calling context should align with the formal names used in the definition of the function in the natural language channel. And why are these things aligned? Well, because developers use both channels. And some of these interactions form constraints. So to illustrate this notion of constraints, let me violate those interactions. And here's an example, the same code minified. So minified is sort of a poor man's obfuscation. It's used more as a compression in practice than obfuscation. But anyway, I claim that if I showed this to you, I hope you would agree that you'd have more difficulty realizing that this implements the sieve of Eratosthenes. Yes? And I think, I could just replace the name with A as in the last example, but worse than replacing it with a meaningless name would be to pick a misleading name. So here I've used Josephus, and Josephus is and also a problem from antiquity where 41 people were arranged in a circle, and every third one was killed. And the game is to pick your starting where you should line up, such that you'll be the last person standing. And I hope you see that, two problems that both relate to sequences, both from antiquity. The antiquity part wouldn't matter, but the fact that they both are over sequences would probably take you a while to overcome the prior of believing in that name. And then, here's an example of confusing typesetting now. And look, yeah, you're making my point for me. Thank you. Now, this is Python, so sure, you can't actually do that in Python. I was playing loose and fast, but here's an example of valid Python where the typesetting is still confusing. So even in Python, which is a white space sensitive language, there can be, you can violate human expectations about typesetting. And the actuals can be misaligned. You can send them in the wrong order to a function. So and here, n is, here's the actual signature for the range function. And n is typically used in the natural language channel to denote bounds. So it's highly unlikely to be the step. It's more likely to be the stopping condition. And I is usually a loop control variable. So it's more likely to be the step. So to understand where these interactions are arising, we turn to Shannon's noisy channel model in psycholinguistics. So here we have a speaker. The speaker's goal is to communicate a message across a noisy channel to a listener. And so their goal is to find an encoding that maximizes the chance that the listener gets the intended message. And in our setting, the speaker is a developer, and there are two listeners because we have two audiences, a machine and a developer at another point in time. So formally, what the speaker or developer here in our setting is doing is they're maximizing this conditional probability. They're maximizing the probability that the intended message is the received message conditioned on the encoding chosen. And because we have two different, we're maximizing this over two channels, the encoding is a pair. It's pairing an encoding for the natural language channel and the algorithmic channel. And these constraints and interactions are arising because this optimization problem is one where the two channels are synergizing. Where if I intentionally, if this relationship were antagonistic, then I would code that violated, where the natural language violated the AL constraint would be easier to understand. But I hope I've convinced you through examples that that's not the case. So these are jointly optimized to synergize. So, but there is an asymmetry here. And that is because the machine to date ignores the natural language channel. And it simply doesn't care. This theory that I've just presented was published at NEAR a few years ago with my co-authors shown here. So to date, research has tended to look at each channel in isolation, neglecting how they interact and constrain each other. So dual channel constraints seek to end this splendid isolation, as we see here. And I'll give you some examples. But first, let's step away from software engineering and look at linguistics. So a seminal problem in linguistics is the problem of answering the question, why do people choose to say things in the way that they do? So in English, speakers hugely prefer saying bread and butter to butter and bread. Now, but if someone chose to say butter and bread, we'd have to ask ourselves, is it a mistake or a joke? If it's a mistake, then we're learning something about ordering, but if it's a joke, then we're not, right? The problem in natural language that has impeded progress into answering this question is that in natural language, word order choice is semantic. Just the ordering is semantic. I could have picked this ordering to imply a joke. In code, some code is commutative. Some code is functionally or semantically equivalent. And here's a simple example. These two expressions are semantically equivalent. And so we are able to use program transformations to build semantically equivalent expressions in code and use that to investigate this question in the context of code without worrying about the confound of the reordering changing the meaning. So my co-authors, Emily, Casey, and Prem, conducted an experiment looking into just this question. So they recruited a collection of Mechanical Turk people with Java knowledge. They trained a large language model. It's not large, and I shouldn't have said large. By today's terms, it was a small language model on a corpus of Java code. And they built a set of trivial, very small program transformations to build a collection of equivalent expressions like this one here. And the research question that they sought to answer was, is comprehension, is human preference and comprehension of code correlated with surprisal? Surprisal, the information theoretic measure of surprise. So after the language model was trained, it unsurprisingly finds this expression to be less surprising than this one. So to a first approximation, we'd say this one is more probable than this one. And when they compared, when they gave Mechanical Turks the same expressions, they found that indeed, when asked which pair they preferred more, humans prefer the less surprising code. They prefer this one. And what's more, they comprehend less surprising code faster. So they were able to, when given bindings for these variables and asked to evaluate it, they were able to evaluate the less surprising versions of the expressions faster. Now, this example I've pulled out from their paper is an extremal case where the median, it took the Mechanical Turks 22 seconds more to evaluate this expression, the more surprising expression, than this one. And I find that in itself quite surprising. They don't look like they would cause a 22-second difference on median difference. So two questions arise from this for me. One is, why is that? Why would there be such a big delta on such a simple expression? And then the larger, more important question is, how much of this result can we carry back into linguistics, into answering the linguistics question about human preferences over ordering of utterances in natural language? Coming back to software engineering, dual channel constraints are useful to us in two ways. First, they're an untapped data source. Data is the new oil. We're always, especially in scarce data regimes, finding another way to extract data and signal from code is useful. Second, there are means for ending that asymmetry that we mentioned, that I pointed out before. They're a way to teach the machine to read the natural language channel and flag up discrepancies between the two channels. So, And so DCC can be applied to the usual tasks. I've just picked 3 here: summarization, traceability, and code generation. So for summarization, an example of a dual channel constraint is that the error handling code in the AL channel should align with the precondition comments. So here I've shown a comment with a precondition and a comment, and this aligns with this one. Well, yeah, these two align, but this one has no appearance here. So we have a violation here. The precondition isn't fully reflected in the code. Another example is in traceability. I claim that topics extracted from a semi-formal specification. So if we use LDA to extract topics, they're going to, because of dual channel constraints, they're going to tend to share tokens with the code that realizes a particular requirement. So we could extract topics from the specification, topics from the code, and a sufficient similarity between the topics would be a way to recover traceability links. I haven't done this. I'm just claiming that this is a possible use for, this is a way to think about a seminal problem in terms of dual channel constraints. And then finally, in code generation, dual channel constraints imply that we should prefer candidate patches that simultaneously minimize surprise over both channels. So to illustrate that, I'm going to talk about this paper that appeared at ICSI this year and won an ACM Distinguished Paper Award. So the core, after you've localized a bug in automated program repair, so we've got we know that the buggy line is here. The central problem of automated program repair is what should we replace this with to fix the problem and not introduce any new bugs. This happens to be an actual bug from the Python black formatter documented here. So a classic way to solve this problem is to use a repair template. And so to divide the search into 2 phases. First, find a repair template and then instantiate that repair template. So a repair template is a parameterized program transformation. And an example one is shown here in orange. And the 2 holes here are its parameters. And in this case, they're variable holes. These 2 holes are intended to be filled with variables. So after you've selected, assuming you've selected the correct repair template, so you've selected a template for which there exists a way to fill the holes that will solve the problem, the search space remains quite large. So just considering the second hole and only considering dereference expressions of up to length 2. So a dereference expression is like root dot left dot right dot leaf, something like that. So considering only 2, there remain over 600,000 possibilities for this hole in the black code. The standard automatic repair model shown here. So we assume that we have a patch generator that we feed a buggy program with a set of suspicious lines. And the patch generator interacts with a patch prioritizer to yield candidate patches. And each of the patches is then checked. And if it passes the checker, it's a fix. And if not, we feed the result back into the generator, which will then yield another candidate. A pioneering work in this space is GenProg. GenProg is a genetic algorithm which used genetic search to yield its generated patches using genetic search. And it just did that non-deterministically. It doesn't have a patch prioritizer. Coconut is a more recent work that views the program repair as a translation problem, a translation from a buggy version to a fixed version. and it used neural machine translation to solve this problem. So it trained a collection of NMT models that differed in terms of their training data and in terms of their hyperparameters, and then combined them into an ensemble. Prophet is the first work that introduced using program transformations, and it prioritizes these using maximum likelihood expectation. And then Trident is work by me and my co-authors using program transformations or templates like Prophet. It has a prioritizer, but it minimizes side effects. So Trident's claim to fame is to be the first APR tool that produces patches that are side affected. And we wanted to produce the ones, we wanted to prefer those that introduce the fewest side effects. What I'd like you to notice about all this prior work is that none of them explicitly prioritize variables. Only Coconut implicitly prioritizes them, and it does so in the soup of parameters of its neural models. So what RETE does is it takes the patch prioritizer and splits it in two, a template prioritizer and a separate variable prioritizer. Its variable prioritizer rests on exploiting first dictum. First said, "You shall know a word by the company it keeps." Now, we're in the code context, so we care about variables, not words. And let me give you some examples. So consider value. Value is it's too generic, right? We can't infer anything about it based on its name. But if I showed you this statement that used it, this use of value, well, this is both a use and a definition. This definition, you could infer that it ranges over the interval 0 to n, right? And here is a dereference expression. Again, very generic. Leaf and type are extremely generic. But if I showed you this expression, then it's reasonable that you could infer that it holds constants from an enum defined in token. So there are two. So from first dictum, we have this goal of characterizing the company a variable keeps, and there are two ways to do it. The preferred canonical machine learning or the neural technique, which is don't just feed it raw tokens. If you feed it enough raw tokens, you'll get ChatGPT and it'll work. It'll do this task and other tasks, right? Through emergent behavior. And the other is more traditional from software engineering perspective, which is let's help it out. We're in a sparse data regime. Let's do some feature engineering to better leverage that data. So using the raw data stream, we just fed it the raw tokens. And here, I'm just draw your attention to depth. Depth is defined here, and these are 3 uses of depth. So in general, for large language models, they're pre-trained by masking all the tokens and recovering them. But in this case, for this setting, I'm interested in variables because I want to train the model to prefer to recover variables. So I just masked out the variables. So I trained it by masking out, say, this one, and then training it, rewarding it for recovering that use of depth. And it did pretty well. So the entire search space is all the project variables that are in scope at a whole, all the module variables that are in scope at that whole, and all the dereference expressions that can be built from variables that are in scope at that whole up to link to 3. I mean, because clearly this is infinite, so I trimmed it. So that's this search space. And the model that I just described over raw tokens, that I trained over raw tokens, it was able to discard 80% of the search space. So it was able to consider just 20% before finding the first variable that fixed the bug, conditioned on having fixed a template, on having selected a template that could fix the bug. But testing is expensive. 20% of that search space doesn't move the dial. It doesn't make APR industrially relevant because of the cost of testing. Many companies that I consult with don't run their entire. Many companies don't do much testing at all. They just do ad hoc testing, and they have a handful of tests. But those that actually, I don't know what I did. Those that actually do have good testing practices actually have test suites that are so big that they can't run them. They have different regimes for running them. They have like a 10-minute regime to run during the day. They have an overnight regime. They have a weekly regime, a monthly, and some of them have even longer cycles. And some of them don't run their entire test suite at all. So an 80% reduction is not enough. Can we do better? So let's look at what's happening with the raw token stream. It's restricted to, it has a fixed window width that we're feeding the network. And that fixed window can span agrammatical snippets. So it could be covering the bottom of one function and the beginning of the next. And the definition might slip out of the window. So def use chains are a data structure from the early in the IT revolution for compilers, where you consider a definition as the start of the def use chain, and then every use is a link in the chain. So I've got in yellow a def use chain. So here's where I'm going to leverage the dual channel constraints. I claim that variable names that appear in def use chains, that appear in a use, are going to be aligned in a way that that these lines have more information than the lines that aren't related to, that aren't in a use. And thinking about it more, that's not quite. I'm forgetting an important set of variables friends, and those are the variables that appear in control statements that govern a particular use. So I call this data structure conditional def use chains, or CDU chains. So to train a model to use CDU chains, we took a pre-trained model. This used to be large, but now it's small. And we extracted lines that participated in a CDU for each hole. And then we masked out, as before with the raw model, I just masked out variables to fine-tune CodeBERT to create RETE's variable prioritizer. Here's our corpus. 4 million. Here's the total number of variables, ignoring dereference expressions. They're popular projects, and the setup is the ML setup is standard for in academia for machine learning these days, which is to say, very small from industrial standards. Okay, so this is the example that I showed you earlier, but with a little bit more context, the statement that immediately precedes it. So this is the bug from the black Python formatter, and here's the buggy line. So in the first step, RETE selects a template. And to do that, it uses the plastic surgery hypothesis. It basically looks in increasingly wide window for statements near the buggy line that could be slotted in. We have a scoring function for that. And then in this case, it selected the condition that preceded it and added a hole to the end of it. So that template basically hypothesizes that the dereference expression wasn't long enough. And then at inference time, we give it the snippet with the template in it. And then the number of CDU chains that can reach that hole remains too large to be useful. So in the Python code, we had 5,600 CDU chains that still reach the hole on average. So what we did was we took a subset of them, And we solved the NP complete problem max coverage to pick those CDU chains that covered the most different number of variables, and then projected them back on the source code to get a subsequence of the source code and fed that to the prioritizer. So, and in this case, what it did was it picked this field of this structure to fix the problem, and that is the correct fix. So what happened in the buggy version of the code was the developer checked for an NPE. So they wanted to make sure they wouldn't NPE, but they forgot that having done that to actually consult the needed variable to see that they were in the right place in the state machine. So how much do DDU chains help? So they help quite a bit in Python, but just a little bit in C. So this is just DU, and then adding C to U, we get an order of magnitude, and the two are much better. Yeah, go ahead.
So something you said a few slides ago, you solved the NP complete problem.
We didn't solve it. We don't solve it. If I said solve, I misspoke. We approximate it. We use a greedy approximation to it. Yeah. Yeah.
You just kind of threw that out there.
No, yeah, no. That was yeah. An egregious misspeaking.
Okay, thanks.
Okay. So we're missing a baseline. These are all essentially ablations. Well, this is a naive baseline, but these are this is an ablation. So we looked to the standard go-to for baselines in machine learning, which is random forest. Here are the features that we use. These four encode the whole. These are directly concern the variable, and when we trained that, it did surprisingly well. So a much simpler model that doesn't require as many parameters did surprisingly well. And this slide gives the results for this year's ICSI paper. But we didn't stop there. Oh, we did. No, sorry. I'm thrown off by I solve NP problems, and I should have told you this talk should have been about me solving an NP complete problem, so I could win the P equal NP question. And get the is there $1 million award for prize for that? Yeah. Well, they give me the Turing, and I get lots of money for it. So that's the talk I should have given. So what do we win from speeding up instantiating templates? Here's the win. So here's prior work, and this is the mean size, number of variables, number of instantiations it needed to consider before it found a fix when a fix was within the ambit of the template, and we reduced that to 4,000. So there's a 14 orders of magnitude reduction in the number of candidates that we needed to consider for instantiating templates. So it's not as cool as solving an NP complete problem, but it's a pretty good reduction. Yeah. Yeah. So I'm using it. I'm using it to. Oh, thank you. So what is the difference between the random forest and the CDU chain, and where are you using it? Are those the two questions? Yeah. So the difference is that the random forest has a fixed set of features up front that I showed here. Whereas the neural network is feature engineered only to the extent to which I fine-tuned it only on CDU chains, and I restricted the masking to be 4 variables. So I restricted the neural model from a feature engineering point of view by my intuition about what training data to expose it to during fine tuning. And here I have an explicit set of, yeah. Okay. So what do we get? Well, what we get is we get 3 more unique, we increase the state of the art in the number of bugs we can fix. So we're at 20, and of these 25, 1 involves a non-local variable. So previously, all fixes involved a local variable. So either a formal or a local in the context, or a global that was already used in the context of the buggy code. So within that function body. So here we found one where it's a global that wasn't used in the local context. And here we found 5 that weren't used in the local context. So this was, we were really, this was what we were aiming for in this work. And it was, an advance at the time that we got it, which precedes ChatGPT by a few months. And I'm going to show you a result in a few minutes. I'll show you just how well ChatGPT does on this problem. And the upshot is it can also get non-locals. So that was the state of the ICSI paper. But we remained interested in the problem. We remained puzzled by why the random forest worked so well. So we thought, we did 2 things. We thought, hey, let's use XGBoost instead of a random forest. And let's add another feature. Let's add a co-occurrence matrix to the feature set. And doing that, we got another order of magnitude improvement. And all I can tell you right now is more study is needed. So in November, ChatGPT came out and had the fastest adoption of any online service. I think Threads came close, but not quite as fast. And Threads is already dropping off, and ChatGPT it hasn't so far. And what we thought is, let's see how well ChatGPT does generating repairs and via its implicit prioritization of variables. So we don't know exactly what it's looking at, right? But variables are in its ambit within its training data. So it's going to be using them to some extent, although we don't know by how much. So this is the template, the prompt template we use. So we would give it the whole snippet, and then we gave it this text. It has a bug at the indicated line, generating a new version that fixes the bug, and then we added an explanation. So there are already 10 papers that have been published or that are on archive that have applied the GPTs to program repair. So this little experiment is not novel in that sense. We differ from them in that we added this explanation. And I'm reporting it to you because it's also on our data set, so we could compare it directly with RETE. So here's a concrete example. So for this bug here in our data set, here's the full function that we give it the full function, and we say it has a bug at this line, and then the explanation we gave it was the issue is that the code has is the length of input shape, which should always be 2, which we infer from this assertion. So we built these manually over the data set. Not all of the bugs it wasn't easy to come up with a simple explanation for all the bugs. So we operationalized simple bugs as those that we could state in a single sentence and that only referred to variables and constructs in that snippet or in the standard modules. And then we just said all the other ones were complex. And in the event of complex ones, the explanation we gave was the issue with the snippet is that the following test case fails. And then we just gave it the raw test case in that case. Chat in ChatGPT refers to its ability to have an extended dialogue, which is built up by extending the prompt. And so we wanted to evaluate that capacity as well. So when it failed to generate a correct answer, we continued the dialogue by prompting it with it's incorrect because, and then we gave one of these three reasons. And here are the results. So here are the two this is single query ChatGPT, and here's the having a dialogue of length 3. What we see is that the GPTs are able to resolve 13. They're able to find fixes for 13 that RETE is unable to, and RETE is able to find fix 18 that the ChatGPTs cannot. So these, and of these, 2 involve globals. 5 here involve globals. So our claim to fame to being the first or the only to come up with fixes that had globals in them has that crown. We didn't hold it for very long at all. These are have an interesting characteristic. They're the bug is easy to explain in natural language, and they typically involve modules. So the solution typically involves either a variable or a function call from a module. And these are involve dereference expressions, so that are domain specific. So it's easy for us to search them. And our variable prioritizer is sort of optimized for that. Our templates generate longer and longer dereference expressions that we are able to effectively do a beam search on. Non-local means, so the question is, what's the definition of a non-local variable? So all of our fixes are in the context of a function body. And in that function body, we call a variable local if it is a parameter, if it's a local variable, or if it's a reference to a global that statically existed in the code at the time that we were fixing it. And all others are non-local. Okay, so RETE assumes that dual channel constraints are in sync. And effectively, I'm resting on the competent programmer hypothesis here. And because it's the competent programmer that makes sure that their names are not surprising, that aligns them. Unfortunately, even the best, to err is human and to forgive is divine. And so even the best of us make mistakes. And there's also bit rot. Correct code can go wrong because the language ecosystem changed or libraries changed. So what I'm saying is that the 2 channels can fall out of synchronization. These are akin to the violations that I opened the talk with to try to illustrate to the concept. And these kinds of desynchronizations can include Trojans, misleading names, and stale comments. And I claim that dual channel analysis can detect and report such inconsistencies. So I'd like to give you 3 examples. So the argument selection problem, I'm going to give you an example of it. So this is the equation for the volume of a cylinder from junior high school. And here's some Python code that implements it. And I've declared some locals to pass into it. And then I invoked it here, and this volume doesn't match that volume. What went wrong? Yeah, I swapped the variables. So the type system can't tell me that I did that because both the variables have the same type. And I claim that here's where this is an example of a dual channel, a violation of a dual channel constraint, because I claim that this is an abbreviation of radius, and H is an abbreviation for height in the natural language channel. So that if we performed a dual channel analysis and ran it as a pre-commit script, it would flag up just these sorts of inconsistencies. And yeah, And we can, use the name information in the natural language channel to map actuals to formals. And so this was done by Andrew Rice et al. And deployed in Google's error prone, where it continues to be used. And it catches thousands of errors per year. This is where it was published. Dual channel constraints imply that code that communicates different meanings to its two audiences may be defective or malicious. So an example would be an Android app that performs some user interface operations. So it asks you, it's a banking app, and it asks you to display, for permission to display the balance or to transfer between your checking account and your savings account. And it does that, but it also does something else, like send your SMS. So this would be an example of a dual channel constraint, because what you see in the interface, what it's telling you in the natural language channel is inconsistent with what it's actually doing. So Hung et al. Built a tool called Asdroid that detects just this sort of thing, and they found an application in the wild, a calendar application that did this with their tool. Another example is when stale comments. So this comment is talking about it's a comment obligation, if you will, not quite a proof obligation, but a comment obligation that this code uses XML, but in fact it's using JSON. And Lin Tan et al. Wrote a tool to do this way back in 2007. So this pioneering work implicitly used dual channel constraints. What can we do to write better software faster with armed with explicitly searching for dual channel constraints? Thank you. I'll take questions. Go ahead.
I have a high-level question. When you were, I think my takeaway from the talk is that you're looking at a program and you're concerned about sort of what it's saying to a programmer, as well as how whether it's executed correctly or quickly.
Do you want to give him the microphone? Because I'm so
Get off my.
Okay.
And on. Yeah. Okay. I'm just going to ask the quicker version of this question. So when you were deciding how to formalize this or how to think about this, why channels? Like, why do you think of it as, like, when I think of channels, I think of something that it has a flow, it has an order associated with it. So why do you think of these as channels?
It's because of I'm going from, because I immediately thought of Shannon information, and it does have a flow, and he called them channels. So that's the why of it, and then nothing deeper than that. So it's just this way back here. So this is Shannon's noisy channel model. He called it an information channel.
Right.
So this is just the nomenclature that was used in the bells for sending information at that time.
Right.
And so,
okay. So why do you choose to think of programs like a channel? Like, what is
it is a medium of communication. And each token, you can view it as as a transcript of a sequence of tokens being passed on a channel from the author to the reader.
Okay, I just wonder, like, so what do you think the sequence is? Like, for the human, what do you think the sequence is, and for the program, for the computer, what do you think the sequence is?
I'm kind of like, is that a trick question? It's the sequence of tokens in the source code. So
the sequence in which they appear in the text.
Yeah, like, well, I mean, humans. I mean, it is the case that we know that humans skim read, and they don't read in a strict linear, left to right, token by token fashion. And that exactly makes my point that the two models are different. Like I said, that humans build to a first approximation, they build a gist of it where they're glancing at things. So I'm not an expert in human reading, like I bounce lights off of human eyes and look at how I think Wes Weimer has done work like that, but that doesn't to my mind, that doesn't undermine my argument. The human is doing, what humans differ from machines in that we vary abstraction levels really quickly, from really detailed to very abstract, and that would be part of how a human converts text into a sequence of, abstract symbols that is a channel. But yeah, I think did I answer your question?
Yeah, I'll think about it. I think so, yeah.
Okay.
Since you're on the slide. I understand wanting to maximize the natural language channel. I don't understand what it means or why we would care to maximize the algorithmic channel, right? Like the algorithmic channel is going to be syntactically correct or not, right? It's going to be correct or not. Like, is there something to maximize there?
Like the experiment different, there are many different expressions that are equivalent, like in the, like these two. So you're going, you're going to pick, I think you're going to pick, like if I could give you a tool that said, if you write the code this in an obfuscated way, or if you write it in this clearer way, and I'm ignoring the natural language channel, you'll pick the better way to write it, or you would tell your students to do that in your software engineering class, because they're going to have to maintain it. It'll speed their ability to understand the code later.
But is that not the natural language that
No,
we're
'cause,
optimizing?
even if we remove, we just replace this with X. We just operated over the minified version. If we're just looking at it from a minified version, there are semantically equivalent ways to write the code. Like you could write the code to add 5 to a variable. You could do X plus equals 5, or you could do X plus equals 1 and then do some other stuff and X plus equals 1 and do some other stuff and X plus equals 3. And that would be that's in the algorithmic channel, but it isn't. It obfuscates that your goal is to just add 5.
Right.
And I claim, for at least as I model the problem, I think that's in the algorithmic channel.
I would have thought that was, admittedly, I know nothing about AI. I would have thought that what we were trying to do was optimize the meaning for the human who has to read it, right? So that we reduce cognitive load. And so that's what you're seeing here. And I agree, the computer is going to care less about how it's phrased, right? Other than if it actually affects the, the computation complexity.
But I claim that the human is looking at both, not just the natural language channel, but the algorithmic channel. And I just gave an extended example, which and maybe you're right. Maybe I'm thinking about it in a broken way, but the way that I'm thinking about it is that incrementing a variable by 5, if I do it in the way that I claim that's in the AL channel. But it's just a particularly goofy way to do it. If it's an intentional, the computer wouldn't care. I mean, it'd be less efficient. It's semantically equivalent, but it doesn't have any. It's not going to change the formatting. It's not going to change the control flow. So it's not going to change the variables that I use. It's not going to change the comments. So for my mind, that is an example in the algorithmic channel.
Been informed that this crazy mic is on. So be warned that everything you say is being recorded. And I've also been informed that I no longer need to bring this around. So if you have a question, don't need to
Shout out.
Now everybody is very careful.
Yeah. John, there's also undefined behavior, and that the human has to make a probabilistic decision about what they think how that works, and I think that's another source of noise and another reason to be worried about optimizing the AL encoding.
I have another question for you. So you mentioned the practical.
I was wrong earlier. I did solve P equal NP.
Oh, okay.
We have it on video.
So this, you mentioned this practical problem that people in the industry who have very large test suites, they run very small subsets, and often it's time boxed. So they'll say, I have 10 minutes to check this commit. I'm gonna pick based on my gut feeling often, my experience, I don't know what yours is. I'm gonna pick the most important tests that I can fit into these 10. And all the results you were showing for RETE, is it RETE or
RETE?
RETE, okay. They were in terms of search space reduction. Do you have an idea of like whether you're able to fit this in like a time box yet?
No, haven't conducted that experiment because
It'd be really interesting because I think there's a prioritization aspect. Right now,
we're not really considering it. I mean, there, like in our data set, there's 107 bugs, and we got to 29. So like, we're moving it by like 7 bugs, but that's still far from 107. So our focus is sort of still on pushing that up. But because let's say we were really fast, no one would adopt it at the current. I mean, maybe not. I mean, I don't know. Like, if those 29 bugs are representative of an important class of bugs, then maybe they would do. But if it were just if the 107 are just uniformly sampled from the space, then I'm not. I guess if it were free, it'd be used. But right now we're focusing more on fixing more of them. But you're right. At some point, you then if we get that up to 70 or 80, then percent, then figuring out which ones would get the biggest bang for the buck would be, and that would fit into the time slots would be important.
the other questions, I should go back over there to check the online audience.
So in this, related to this bug question, right? So in the hierarchy of these bugs, like, I mean, you know what all the bugs, right, in the test set, like,
Yeah.
Is there, can you isolate any feature that doesn't find those other bugs? Like, or are they also, just following up on this question, right? Are they more relevant, or are you just kind of finding like the easier bugs, or is there a ranking of these bugs that you just, or is kind of the pattern a little bit, because you're able to identify kind of what ChatGPT can do that you cannot, and also what you can do that ChatGPT doesn't, right? Which is related to like, oh, they have more general language methods and yours is more domain specific. But with respect to the bugs, like, is there any kind of classification of these bugs that
There are papers that have done that, but we didn't do it on this data set.
But then on like those papers, like, do you know in their classification, do you know where your framework fits?
No, we didn't do that work.
Okay, no more questions online. Yeah, go ahead.
Is it possible that the model can generate why it thinks that this patch is the most probable solution for this bug? Because it has access to the natural language channel.
So can you restate that question? Sorry.
You are prioritizing the patches like that would solve the bug, right? But can you generate the causes why the model thinks that this is the correct patch?
Oh, you offer an explanation.
Yeah.
We haven't investigated that question.
Is it possible because you have access to the natural language channel that may have something saying that this is the correct patch?
Yeah, we would have to do separate engineering to do that. We've thrown at the time at inference time, we've thrown away the CDU chains that are. I mean, after we make the prediction, we haven't kept them around. And yeah, you'd have to do some kind of delta debugging or ablation of the inference CU chains to try to haven't done it.
I'm not sure if it's relevant. Can you go back to the slides where there's 10 over? Comment.
I comment. At the
Right,
very,
yeah, I comment.
I mean, I'll just do it here. This is. What is the command for? Is there a command for
I think if you type.
Let us search for Cam.
if I type in, I don't know what the number is. 80. No, there.
Yeah.
Yeah.
Yes, he's there.
The comment was saying rate from XML and the code is doing JSON, but what if the comment is wrong?
I mean, I hope I didn't imply, I hope I didn't make another misstatement where, I mean, dual channel constraints doesn't say which channel is, is
Or
correct.
just simply point out like it's not consistent.
Yeah, there's an inconsistency here. We don't have the ground truth as to which one is, yeah. Is it, I mean, is it a stale comment? It's probably a stale comment just from first principles. Because comments are not, there's nothing that forces us to update or validate comments. So almost certainly it's this comment, the comment that's stale. But it could be the other way around. I mean, but I would, my prior is that would be unlikely.
So there are no further questions. Let's thank Earl one more time.